Okay, now I would like to invite here to the stage the founder at Port 179 Ltd, BGP Tools, Ben Cartwright-Cox, with the title of his presentation that sounds like that. Go along, weird signals with optics. Give him applause, please.
Hi, everyone. Hi. Oh, these are my old slides. Okay, I will make do with what I have. Cool, so hi, I'm Ben Cartwright-Cox. I run something called BGP Tools. If you don't know what BGP Tools is, it's basically a BGP looking glass for debugging on the networks. You may remember me from other blog posts way back, something like BGP Battleships, in where I play the board game Battleships using purely BGP messages. And I also do a bunch of reverse engineering of various hardware devices in my spare time. The core of this is I really just like knowing how stuff works. It makes life more interesting, and I don't like taking technology for granted. My rule of thumb is, if you have an object that you don't understand why it works, it's either very smart or very stupid. And I would really like to know which one of that it is before I depend on it. So the modern day internet is almost entirely all optical. And the optical networking kit is a bit of a weird world. You have the devices, which support one set of standards, the optics, which support various shapes and sizes, and then the actual laser format that comes out of those optics, which also supports various shapes and sizes and wavelengths. And of course, the cabling is all different. Most of the world is moving on to, or has moved successfully onto single-mode fiber, but there's a lot of multi-mode around of varying quality. So what does that mean? That means that your average boring ISP network uses SFP plus optics on switches or routers. Probably they have bought their vendor optics, either because their vendor has locked them down into doing so, or if they just haven't discovered the cheap third-party suppliers yet. The switch chip spits out some standard 10 gig MMI signal towards the optic. The optic turns that into optical light. The opposite happens. Data bits happens, cat videos are exchanged, or whatever your users are watching. Some optics are surprisingly stupid. We're going to briefly ignore the ones with full CPUs in them. You can buy optics with full Linux computers inside of them for things like VDSL modems, ARM machines. One of the middle one is, I'm pretty sure, designed for spying on customers or maybe not your customers. And for some reason, the last image. But you can also buy GPON ONTs entirely packaged in SFPs, and those also run Linux inside the optic. But remember, some optics are surprisingly stupid. There is also an EEPROM in there to tell you the branding and things like that. There's also a microcontroller in there to tell you things like the temperature and the laser light coming out of the optic. Your average faster boring network is not that much different. Uses a QSFP28 optic on a switch or a port or a router again, probably buying the vendor optics again, and depending on the optic, because 100 gigabit is a complete mess of standards, various fancy chips are used to convert the signal that the switch takes out into the physical light form, maybe even coherent for long-haul data transfer. Once again, the opposite happens on the other end, and I don't know, cat videos are exchanged at 100 gigabit speeds. Some of these optics are surprisingly smart. They involve digital signal processing, which, depending on how old your laptop is, these optics probably have chips with smaller feature sizes on silicon than the CPU in your laptop. Some of these chips are breaking now 3 nanometer feature sizes. And you're installing these in the hundreds, depending on your size. So some of these things are very smart. Obviously, other optic form factors are available. If you're running on the more legacy side of equipment, you may still have equipment out there that uses XFP, CFP. If you're running on the newer side, maybe even the InfiniBand stuff for the AI people, you're running on like the OSFP standards. If you're really old, you're using X2, ZenPack, etc. Of course, there is not only that for the optical world or for the networking world. We also have the home stuff. On the back of your hi-fi or sound amplifiers, you will see these optical inputs and outputs. This is kind of an interestingly weird standard. This has existed for a very long time, and it's called Toslink, or SPDIF, but I'll call it Toslink. There are two kinds of people who use Toslink. People who have ground loop issues, where effectively electrical interference means that there is a hum in all of their sound output. And then there's the other kind of people who want to look very cool by having some kind of optical system inside of their sound system. Toslink is very slow as far as all optical protocols go. It runs at pretty much the maximum of 10 megabits per second in its configuration. But in realistic, if you're sending stereo audio down it, probably only does 3 megabits. The wavelength is just effectively a red LED, and the optical fiber is basically just a 1 millimeter thick plastic core. Because of this, and we'll get on the reason why, the maximum cable length is about 10 meters. Obviously, the core on a single mode stuff, the stuff that we're using today is like 9 micron. Yeah, sorry. And the reason why this matters is that optics are strange in that the thicker the core is, the more your signal gets torn apart. So if you're sending pulses of light down a optical tube, effectively, because you can never insert the signal perfectly down the thing, the signal just gets ripped apart. And unfortunately, the animation I have here doesn't work, but effectively, these pulses almost become unintelligible at the end. So anyway, if we have Toslink and we are limited to this annoying world of 10 meters, I was thinking, so these things are too stupid to care. So is it possible to make 10 kilometer Toslink? So we're going to need to do some things. If you go and look up the standards, and these are all open standards, you can look at them freely on the internet. This is the MSA. This is effectively the standard form factor for what an SFP optic should look like. We're going to remove some of these pins because we won't need them. The ones that we are interested in are delivering power to the optic and delivering data signals to the optic. We don't particularly care about communicating with the optic because we don't need to ask it how hot the laser is and things like that. So, yeah. A friend of mine made some of these experimenter boards. These things are great for playing around with. These boards contain effectively everything you need to just play around with these optics. They contain basically a power supply for them. They contain the cage, the connector for the optic, various debugging pins, LEDs to tell you that you've broken something or blown up the optic, and critically exposed pads and line drivers. Line drivers are super important because while your standard digital signal looks like this, actually on higher speed systems you need to make them balanced or alternatively a differential signal. This is important because if you've ever, doing it this way effectively means that when you are running high-speed signals down, the signal doesn't get as easily interfered with by other signals on the board. Because the general rule of thumb is the faster your signal goes on PCBs, on the actual circuit boards, the more annoying habit they have of leaving the board and going onto other parts of your board, which is very annoying if you're an electrical engineer. So this helps prevent that. On the scope, we can see, if we look at just a standard audio signal on an oscilloscope, we can see nothing interesting to see here, an analog signal. If we go and look at, for example, SPDIF, though, we're on a much smaller timescale, but we have this very obvious digital signal. It's about 2 megahertz of data, another animation that doesn't work, unfortunately. So let's do our proof of concept setup. So we have my laptop. Bought some of these Toslink analog to digital converters and likewise digital to analog converters on eBay, put it through one of these boards and put in about 500 meters of spare fiber I had hanging around and some sacrificial optics that I didn't mind blowing up. The final proof of concept, well, it doesn't look very friendly if I was to take it through an airport, but it does work. On the scope, we have in green, we have before it goes into the transmission setup, and yellow is before it enters the transmission setup, and green is afterwards, and we can see there's about, 59 microseconds, which is reassuring because, it's 34 nanoseconds, my bad, which is reassuring because there's about 500 meters of fiber there, which means that roughly the speed of light still makes sense. If it was a lot larger, that would be slightly alarming because where is the signal going, there should be no real processing inside of these optics. If it's shorter, then we might have violated the laws of physics. But obviously, this is only 500 meters. That's not very interesting, because Toslink, in its normal capability, can still do 5 meters. It maxes out at 10. So what if we could go longer haul? So a friend of mine has 2 sites in London, Telehouse and down the road, IB House. They're about, as far as a walking distance goes, 650 meters, or also about as the dark fiber goes. He has between these CWDM multiplexers. So what I did is I convinced him over a drink to let me borrow one of his channels on one of his multiplexers, installed a loopback on one of the sides, and put my magic on the other. Oh, and also borrowed one of his expensive optics, with the impression that if I blew it up, I would pay him back. And it worked. Once again, I don't think the data staff were hugely impressed with this, but it does work, and the portable speaker was also struggling to get above the noise floor of the data center, but it works. On the latency point of view, harder to see this time, because you have to sort of align the bits. My scope doesn't have a feature to do this, but it's about 11 microseconds, which, if you put that into Wolfram Alpha, says about 2.2 kilometers, which makes sense, even though the buildings in a 2D manner are only 650 meters away. Buildings are 3D, and there is a lot of patching involved, and things get busy very fast, certainly in buildings like Telehouse, like this one. So 2 kilometers is cool, but what if we could go longer haul? So typically, you are looking for, if you want longer haul options, and you're doing 1 or 10 gigabit, you are probably looking at DWDM at this point. As I said previously, DWDM is like CWDM, the stuff we just used last time, but denser. The optical channels are much more tight. These optics are much more expensive because they rely on a lot more interesting optical physics involved. To put it simple, they do a lot of interesting heating of the optic, the actual lasers, to get a very precise frequency. It's very cool, but generally speaking, the technology that makes things cool also makes them quite expensive. They also have a useful feature in that they operate in a band which is very good for amplification. Incidentally, if you ever want to go and look in the physics involved in optical erbium-doped fiber amplifiers, I don't understand them. They feel like a bug in physics. It just doesn't feel like something that shouldn't exist. Most of the time, when people have long-haul circuits, they will involve things like transponders. So transponders are fine because they are effectively devices that copy and paste signals from one optic to another without trying to interpret the signal. What is a transponder? Effectively, when you're giving a wavelength to a customer, you don't necessarily want to give your customer raw access to your fiber because they may send the wrong frequency down, they may send something crazily overpowered, but also you probably just don't want them to buy the expensive optics on their end. What you want to do is you want to hand them a standard optic that they probably already have, and then you are the one that owns the strange optic. This also allows you to change these at your will, effectively. So transponders are great. My system has no problem with transponders. There are options that don't work, however. There is a system called a muxponder, or the general broader fancy line system technologies. These do a lot more processing with the signal. They effectively try and understand the signal directly. So that means they take your Ethernet signal, they take the raw Ethernet frames, and they will either speed them up or they'll pack them into a more faster signal with other customers. Because they're doing this, they need to actually understand what they're looking at. Because no line system that I am aware of in existence is capable of understanding Toslink, this will not work. And so I had to go around a lot and asking people, do you have long-haul circuits, and do they not involve muxponders? Unfortunately, in London, where long-haul fiber can be quite expensive, not many people had not many people were left who hadn't converted their systems to muxponders yet. However, there was one. So physical distance between these two data centers is about 6 kilometers. It also happened to be a great bonus because I was in one of these data centers. So once again, this is Telehouse, just a very big exchange, or very big building in London. Probably one of the most critical buildings for London internet infrastructure, or I guess the entire of the UK. And then there's Interaction, the data center that I run my business from. Once again, went to Telehouse, put a loop in place on their multiplexer, and then did the whole same thing again. And it turns out, yeah, pretty easy to do, and it turns out it works. The round trip time was about 84 microseconds, which equates to about 16.8 kilometers of fiber. We're now really far above what Toslink wants you to do. I'm sure no one was actually expecting the standard to go this high, but it seems to be completely fine, using relatively boring standard 10 gig optics, or 1 gig optics, with the added fact that you had to put attenuation in because the optics that I was using here was designed for 160 kilometers. So if I had used them like they were intended, they would have blinded themselves and potentially burned themselves out. But what if we could go longer haul? Intercity. So, LONAP, the second London Internet Exchange, had a spare DWM channel between Equinix in London 6, which is not actually in London, it's in a separate place called Slough, but I guess better branding if you call it London, and then actually London LD8 in the Docklands. This is not only intercity, but it's also so far that it has to involve amplifiers. One way, about 73 kilometers. I didn't actually have the KMZ from the provider, but this is roughly what it looks like. And for those who are not familiar with London, here's a quick map. Am I angry at Equinix? Perhaps. So, pretty much the same setup as last time. We have the other customer stuff, LONAP stuff, which I really hope not to interfere with. We have their mux, their amplifiers, and then the same in the other direction. You may be interested to see, you may be curious in that there is a attenuator on the loop. That is because these muxes, these mux amps, these smart optics ones, they will amplify both on the inbound and the outbound. Which means that if you do a direct loopback, the signal that comes back in will be way too bright for the unit to handle because it's not expecting loopbacks. Although, because this is a much smarter unit, for once, we actually get some cool statistics out of the control plane of the unit. I'm in the way a bit here. But if you just about see, it says that it actually understands the signal and the weird format it uses for the wavelength, and it thinks that our Toslink signal is about 1 gigabit, or anywhere between 1 and 32 gigabit, which 3 megabits, close enough. This is what it looked like, once again, not trying to make friends with the data center staff, but this is what it looked like in person. As I said, we wired it all up, and it didn't work. I built the setup again there using multi-mode cable and confirmed that the wider setup worked, but then once I swapped in the DWDM optic, it just didn't work. I then swapped in the DWM optic into a network card I had hanging around and confirmed that the optic worked. So there was something about this signal that for some reason didn't work. Was it the multiplexer? Was it the optic itself? I put it on the scope, and once again, no animation here, but notice that this square wave, the scope has a function that lets me inject a prescribed square wave into the system. Note that this square wave is not very square. There's that weird notch in the middle. So it turns out that for some reason the scope is just not, or the optic is not accepting signals around 3 megahertz, or about 3 megabits. But it does become stable, as in more square-like, at about 6 megahertz, or 6.5. This is annoying because I have no way of making the signal that fast because, well, in theory I could. If I wanted to take an entire surround sound system with me and put 5.1 audio, then the system would rise to the correct speed and everything would work fine. Unfortunately, bringing a surround sound system into a data center it would raise questions. So I'm not going to do that. So trip failed, go back home, try and figure out what happened. So it turns out if you take these optics apart, finding the chips inside of these is really hard. Even if you do take the chips in, even if you do manage to get the chips, because some of them are just, or actually quite a lot of them are just laser burned off, the data sheets of them don't exist. It's a very secretive industry, I guess. The stuff that goes inside them, not very well documented. This optic happened to be a 10 gigabit DWDM optic. So maybe a 1 gigabit one would work, but it's not obvious to me why. So I sent some emails around, and I would like to thank Flex Optics for giving me perhaps the most detailed answer, or in fact actually the only answer, which is basically at higher speeds you need something called a retimer in these optics. The best and easiest way I can describe it is a retimer makes your square wave more square, because the end device may not enjoy ambiguous signals. So the point of a retimer is to basically make things look better for the end device when signals are getting a bit vague. So, okay, I need to go and buy some optics that do not have retimers in them. How hard can that be? So acquired a brand new set of 1 gig optics. I had a very interesting discussion with the vendor, where I opened the email conversation with, hey, I want to buy some 1 gig optics in DWDM, and they absolutely cannot have retimers. And they were like, okay, sure, the spec sheet here says there are no retimers. Should be all fine. By the way, what signal were you sending? It's like, it's fine, just don't need any, just no retimers. So they arrived, and it was instantly a bad start, because if at the bottom you can see on the PCB it says XE09, which in my eyes states that this is actually a 10 gig optic. In fact, if you Google for that exact thing, you know how I suggested that there may not be many factories that make these things? Well, funnily enough, straight up on Google, all of these are 10 gig DWDM optics, which is not great. And guess what? You plug it in, and it doesn't work. Basically, Fiberstore sold me an optic, which was a 10 gig optic that they had just rewritten the EEPROM to say that it was a 1 gig optic, which is fine. I bet that works perfectly fine for 1 gig communications. It just doesn't work, and is also not what they told me over email. They did take back the optics, though, with a refund, so I guess props to them for that regard. So I finally had to go and start an adventure where I had to hunt for very old 1 gig DWDM optics, which is a very weird thing to search for. Thankfully, there were a few Slack channels that pulled through, and people started looking through their weird bins of hardware that was about to be thrown out. So I ended up with these. These are sufficiently old enough in that they say STM16 on them. And it turns out these actually do work. Went for a second round. And yeah, it works. The difference between the two signals, it was basically impossible to align these signals on the scope. And so instead what I did is I just tapped the signal to see at what point the pulses seem to align. The answer is about 720 microseconds, which, yeah, it looked like that. And I also, so this system works. I heard the glorious sounds of Rick Ashley's most famous song straight through the system. And it also, as a bonus, if anybody was tapping the line, they not only got a very strange signal, but they also got to hear this. I don't know if this line was tapped, but I like to do these things, just to leave some future Easter eggs for my glorious intelligence agencies in my country. Future pointless innovation that you could do on this idea. If the optic itself didn't have something that was only expecting a square wave into it, you could totally just drive raw audio down this thing. In fact, to my understanding, this is how things like RF over fiber works, or RF over glass, RFOG. So if digital, also, it turns out, modern day FM hardware for car radios and things like that don't necessarily care about the waviness of your signal. You can totally drive them just using square waves, which means you could probably send about 100 megahertz FM modulated signals. And I'm pretty sure it would sound like music on the other end. I didn't get to try this, but I'm pretty sure it'd work. It is also really tempting to attach a dial-up modem to both sides. This would definitely create the most wasteful use of optical bandwidth I think you could achieve, because you would basically be using a slice of bandwidth that was fully capable of doing 10 gigabit for about 40 kilobits, sorry, 10 gigabit for about 40 kilobits of signal. I think this would also completely blow the minds of someone in an intelligence agency. The amount of work they would have to do to figure out that I'm doing almost nothing would be glorious. And I'm sure a fantastic use of my taxpayer money. So, to conclude, yes, you can actually send low-speed signals down SFP optics. Most of the time. Most optics start working as long as your signal is higher than 150 kilohertz, but do not like working, some of them don't like working below 6 megahertz, but that's fine. And as a bonus, a lot of these optics can be used very far. Even your standard LX or LR optic can be used for 10 kilometers, they say. So 10 kilometers is a long way. There may be a project of yours that may fit in this. However, there's not a likely very good reason to do any of this. There are better IP solutions for almost every use case that you could imagine where this would be appropriate. But that's not the point of it, right? The point is to learn how and understand how these things work, because what you know can hopefully build a much more informed decision of what you're buying and building in the future. And also, it'll let you potentially create more horrifying workarounds, which will definitely be temporary, right? I know personally way more about optical transmission than I did before, and the inner workings of what goes into these optics, and hopefully maybe you do now as well. Thank you very much. Those email addresses are wrong, but you can guess it.
Thank you, Mr. Ben. It was very interactive and fun, right? And maybe do you have some questions, because we have some time left before we will go for the first coffee break. So if you have one, just raise your hand, and my colleague, oh, I can see one. My colleague are coming, yeah.
Hello, Alexi.
Hi, yes, this is Alexi from Finland. So I think one useful application for something like this is synchronizing atomic clocks.
Yeah, you could totally do that. How would you synchronize it? Yeah, so this is already done to some degree. There are some professional GPS equipment or NTP equipment that will use effectively this kind of technology to synchronize itself, because when you're doing time stuff, it's very important to have as very few devices in the middle of you to the system that's finally receiving the pulse. You should probably actually just buy the vendor equipment to do this rather than build that. But yeah, you can definitely buy the equipment that is effectively doing what I have just done there, but for 10 megahertz PPS signals. You probably also want to avoid a retimer on those, though, because that might mess up your time signal. But yeah, you could totally do that. And it's probably the only remaining good use case of that technology that I just demonstrated.
Thank you. Maybe someone else? Just raise your hand. I can see. Yeah.
Yes, thank you. I am Timur, and coincidentally, I'm also from Finland. What do you think of going beyond the London, Oslo, even connecting continents maybe with some TOS links?
Yeah.
Maybe we can cooperate with that.
Yeah, so it's a really good question. So it turns out, if I had done this experiment maybe 10 years ago, then it would have been totally possible to do this across the Atlantic. The problem is that almost all of the undersea cables for this now are no longer selling spectrum services. They're selling coherent OTN style things where you plug into a wider system, which is effectively a muxponder, as I mentioned, incompatible with what I'm doing. So yes, you could totally do it. And there is some conversations with maybe one cable operator which may be interested in, who's currently doing a build-up service from that route, from across the Atlantic, which I may be able to do. But it may require me flying to the US, and I don't want to do that right now. So it's complicated. Watch this space. There may be a very, very, very big update on this space for long-range TOS-link.
Good luck.
Thank you very much. And we have 1 minute left for the final question, if you have some.
Okay.
Be brave. Okay.
No?
Okay, so thank you very much, Ben.
Thank you.
And now, yeah.